Kirchhoff's laws are two laws that help us analyze circuits and get information we need from different parts of the circuits. The first one is the Kirchhoff's voltage law. Now it states sum of the voltages in a closed loop is zero, while the Kirchhoff's current law states that the sum of currents entering and leaving a node is zero. So we have a circuit formed by these components. We have 3 resistors and we have 1 voltage source, and then we have these 2 points as nodes. Okay, so if we want to consider Kirchhoff's law here, now this is a loop. Okay, this is a closed loop. This is also another closed loop. Alright, okay, so Kirchhoff's voltage law is saying that sum of voltages in this closed loop will equal 0. So let's take this loop first. So he's saying this voltage plus the voltage drop across this resistor plus the voltage drop across this resistor would equal 0. Okay, this voltage plus the voltage drop across this resistor plus the voltage drop across this resistor would give us 0. Then for the Kirchhoff's law, the sum of currents leaving and entering a node is 0. So let's explore this further. We have a voltage source here, and these are our resistors, R1, R2, R3. And V1 is the voltage drop across R1, V2 across R2, V3 across R3. Okay, now we have a single current value going through this circuit, throughout the circuit. The same current goes through the first load, goes through the second load, and the same current goes through the third load. But the voltage drop across these loads differ depending on their resistance. Kirchhoff's voltage law is making us understand that if we sum this V1 to V2 to V3 and sum it up with this voltage source, we're going to have 0. These voltages around this circuit is provided from this voltage source. This is the positive end of this resistor. This is negative. We connect the positive end of the load to the positive end of the source. Okay, so the source feeds from its positive into the positive of the load. All right, then we connect the negative of this load to the positive of the next load, and the negative of this load to the positive of the next load. So if we sum this plus V1 plus V2 plus V3 minus V, or if we take this to be positive V, this will be negative V1, negative V2, and negative V3, because we have the current moving from positive to positive. But then we have it moving from negative to positive for all these ones. So the signs here are the same, while the sign here is different. So we have V minus V1 minus V2 minus V3, or V minus, in a bracket, V1 plus V2 plus V3 will all equal 0. For the current law, we have sum of currents going into a node to that coming out of the node equals 0. So we have I minus I1 plus IS equals 0. So we have current entering into a load, okay, is equal to the current leaving the node. So you see, this is I coming into the load, this is IS plus I1 leaving that node. Okay, so we have I minus I1 plus IS equal to 0. Okay, so if we go to the second node, we have IS, okay, being equal to I2 plus I3. Of course, you see, it is IS that splits into these two currents. So if we subtract both currents from IS, we're going to have 0. Okay, so that's basically what the law is trying to make us understand. So we have the same thing on all these other nodes. So an example, okay, if we have resistors like this connected in series, obviously the effective resistance is the sum of all resistors in this network. So we have 220 plus 330 plus 470, and that will give us 1020 ohms. Okay, so we want to find the current flowing through this. So now, once we have gotten our resistance and we have our voltage as 9 volts, if we use Ohm's law, we can get our current flowing through this circuit as 8.824 milliamps. All right, then we move on to finding the voltages across each of these resistors. So this is our VRO1 and VRO2, VRO3. So VRO1 is equal to 8.824 milliamps, which is the current that flows through it, multiplied by 470, which is its resistance. Okay, from Ohm's law, we know that voltage is equal to current times resistance. All right, that will give us 4.15 volts. So the voltage drop across this resistor is 4.15. Then we check for VR2 and we have 8.824, which is same current going through this. We have this in series, so the same current goes through every load on this network. All right, so we have 8.824 milliamps going through I2 and going through R2. So we multiply that by its resistance to get the voltage across it, the voltage drop, and we have 2.9 volts for that. And then we come to VR3, where we have the same current flowing through it, and so we multiply the current by 220 ohms, and we have 1.9 volts across it. Okay, so now we have these voltages across this resistor. If we use Kirchhoff's law, if we decide to prove Kirchhoff's law with this, we'll see that we have 4.15, which is the voltage drop across this, plus 2.9 plus 1.94 volts. Okay, and that gives us 8.9, which is approximately 9. So you see the sum of the voltages across this loop, okay, is 0. The actual summation we should do in this case is 9 volts. Okay, so if we're taking our 9 volts as positive, remember we talked about the signs. All right, we will take every other one as negative, minus, because the positive of this 9 volts is in contact with the positive of the load. Okay, so their orientation is not same. You can see this has same orientation with this and this, while this one, the orientation is opposite. So if this is positive, every other load will be negative. If you're taking the loads as positive, then you will take this one as negative in your summation process. So we have 9 volts minus every other thing here. Okay, then we can use that to see if our answer would equal 0. So we have 9 volts minus 4.15 plus 2.9 plus 1.94. Okay, all these in volts. If we sum this up, we're going to get approximately 0. Okay, we're going to have 0. So this is what Kirchhoff's law tried to make us understand. Okay, so if we sum it the way it was done here, we'll see that the voltages here will equal this voltage source, but opposite in orientation, so opposite in signs. All right, or we can do this. This is actually Kirchhoff's law being proven. 9 volts minus this voltage drop plus this voltage drop plus this voltage drop. This is the same as saying 9 volts minus 4.15 minus 2.9 minus 1.94. You're still going to get 0. So for KCL, let's try to prove that. So if we have this network of loads in parallel, the voltage across all loads will be 9 volts, okay, because it's parallel, because it's in a parallel configuration. So we have same voltage across all these, while when it's in series, we have same current going through all loads. If we need to find the current flowing through these resistors, we have I1 equal to V over R1. Okay, for I1, of course, from Ohm's law, V is equal to IR. So if we make I the source of the formula, we'll have I equal to V over R. So if we do that for the first resistor, we'll find the current flowing through the first resistor as 19 milliamps. Okay, so we have 19 milliamps flowing through R1. For R2, we have 9 volts, which is the voltage across it, divided by 220 ohms. All right, which gives us 40.9 milliamps. And we have the same thing we have the same process for R3, which gives us 9 volts divided by 330 ohms and gives us 27.3 milliamps. We can see that we have different currents flowing through these resistors, different currents coming into the node, and we have different currents coming into the individual nodes. So our currents divide as they move across the network. So let's now try to find if Kirchhoff's law is true. So we have I equal to I1 plus I2 plus I3. So I1 is equal to I1 plus IS. Okay, so we know IS is I2 plus I3. Okay, we can see that IS comes here and splits into I2, I3. So I2 plus I3 is IS. So this is same as saying I1 plus IS equals 87.2 milliamps. Okay, now if we want to find out the amount of current used up by this circuit, we sum up all these individual currents from the different resistors, the different loads on this circuit, and we're going to have that as 87.2 milliamps. If we try to prove Kirchhoff's current law, we would find out that our I is equal to I1 plus IS. Okay, or we can say I minus I1 plus IS equals 0. So this is Kirchhoff's law for this node. So this is same as taking I1 plus IS to the left hand side. Okay, so we're going to have this I minus I1 plus IS equal to 0. This is Kirchhoff's law. Let's remember our IS is equal to I2 plus I3. Okay, so this means I minus I1 plus IS equals 0. So let's find out. Our I1 is 90 milliamps. Our IS is 40.9 plus 27.3 milliamps. So which is the same thing as 19 plus 40.9 plus 27.3 milliamps. So you see, this will give us 87.2 milliamps, which is the same thing as I. So if we subtract I from 87.2 milliamps, we're going to have 0. So that's basically Kirchhoff's law. So the same holds true for every other node. We have IS coming into this node. Of course, IS splits into I2 plus I3. So if we sum I2 and I3, we're going to get IS, the value of the current coming in here. Okay, so basically that's what Kirchhoff's law was trying to make us understand. So we move on to the voltage divider. The series circuit is naturally seen as a voltage divider. Okay, so if you have a circuit like this, it's expected that this voltage source would have its voltages spread across this circuit over these resistors in a way that the voltages on each of these resistors will sum up to the voltage source. Okay, so that is these loads dividing this voltage into different values across their terminals. The ratio of the voltage drop of a particular resistor to the total voltage of the voltage source equals the ratio of that particular resistor to the total resistance. So simply put, if you have Vn being the voltage across any of these loads, and we divide it by the total voltage on this system, which is the voltage of the voltage source, we can equate it to the resistance of that particular load whose voltage across its pins we considered here, and divide it by the total resistance in the circuit. So let's take VCD as example. So we're considering this resistor of 220 ohms. We'll see VCD divided by 9 volts can be equated to the resistance of VCD divided by the total resistance. Okay, both ratios are equal. So if we make VCD the subject of formula, we can find VCD to be 1.9 volts, which means if you put your red probe here on your meter and put the black probe on the negative, okay, of this circuit, you're going to have 1.94 volts. So if we can simplify our resistances to two resistors like this, so let's say in this case R1 is 470 plus 330, these two resistors considered already here, all right? It will mean that we can find the voltage across this resistor by this formula, V out equal to V, okay, the overall voltage, times R2 divided by R1 plus R2 divided by the total resistance, the effective resistance of the circuit. That's same formula as this. Okay, this is VCD, okay, VCD, which in this case is V out. Okay, VCD in this case is V out, okay, equals V, which is the total voltage, which is here 9 volts, times R2, the resistance of that particular resistor, in this case 220, divided by R1 plus R2, effective resistance, which is 1020 ohms. Okay, so it's the same formula. We also have current dividers, and parallel circuits are current dividers. So we saw in the previous slide that once the current hits any node, it splits into different parts, okay, depending on how many lines are connected to that node. But then the amount of current coming into that node is equal to the amount of current coming out of the node. The ratio of the current through any resistor in the parallel network to the total current, okay, in this case is equal to the total resistance of this network to the resistor of that individual resistor. So if you have a current flowing through any particular load, okay, any of them, we divide it by the total current flowing through the circuit, it is same as getting the resistance of the total network, the effective resistance of this network, and dividing it by the resistance of that resistor that has this current passing through it. Okay, so an example is, in this case, if we take I2 as our resistor we are trying to consider, I2, we divide it by the total number of currents in this circuit, and we have seen that we have 7.2 milliamps flowing through this circuit, total current I. If we equate that to the total resistance, the effective resistance of the network, which we found as 101.52, of course we can find that the effective resistance, 1 over effective resistance is equal to 1 over 470 plus 1 over 220 plus 1 over 330, then make array effective subject of formula, you will have 101.52 divided by the resistance of that particular resistor, 220 ohms. And we have our I2 as this, we simplify that to get 40.2 milliamps.